Okay, so welcome back. Before I start, I'll just remind you what we did last time. We had begun to see the how nice orthogonal sets were. An orthogonal set was actually nicer than, for instance, a linearly independent set of vectors because, well, you automatically got linear independence, right? So any orthogonal set of vectors is automatically linearly independent. And then in addition, you got the statement here that I called the nameless theorem that says that if you have an orthogonal basis for some subspace, then anytime you write a vector as a linear combination of the vectors in that orthogonal basis, you can actually immediately compute the weights, right? There's no need to write out a bunch of, or to write out some matrix equation to solve for the weights. You can actually compute the weights one at a time, and you could do this. Even if you just needed a single weight out of this linear combination, you could just immediately compute that. Right, so this was very, very, very nice. This is an extremely convenient thing to have going on, and so an orthogonal basis is basically as good as it gets. It is very it is something that we're going to be very interested in. The notion of having an orthogonal basis or an orthogonal set of vectors is going to be something so nice, in fact, that we are going to come up with an entire process for constructing these things. Because as we saw, it was easy to check that a given set of vectors was orthogonal or not, because you just compute some number of dot products, and dot products are really easy to compute. But coming up with these sets is actually more mysterious because if you think about the algebra that goes into it, right, if you start building it up one vector at a time, it quickly gets out of hand and becomes really, really tough. So we are going to be working now. Everything we do up until we get to what's called the Gram-Schmidt method is going to be building up the machinery that we need to apply Gram-Schmidt. Okay, so the very first thing that does this is the notion of an orthogonal projection. So there's an entire chapter based on orthogonal projection. So a first taste of orthogonal projection. This is a little bit of a misnomer because, as I mentioned last time, you've actually already seen an example of orthogonal projection before, and that is the example we're about to see now, which is the notion of projecting a vector onto another vector from Calc 3. Okay, we're going to see that example played out here in a slightly more general setting because we're going to be doing this in Rn. So let's say, suppose that given a non-zero vector u in Rn, I want to decompose a vector, say y in Rn, into the sum of two vectors, one that is a multiple of u, this given vector u here, one's a multiple of u, and one that is perpendicular to u. All right. So really what I'm asking is to be able to write y as y hat plus z, where y hat is some constant alpha times u. So alpha is just some scalar. And z is perpendicular to u. All right. So this is what I want to do. Now, you might say, why would I want to do this? So what does this look like in the plane, first of all? So what would this look like in the plane, this problem? So say that I'm in R2 now. So in the plane, I'm not going to write coordinate axes here because that's going to bias my picture toward you looking at those things. So consider this paper as the plane. Okay, and so what am I asking here? Well, I have a vector y sitting in the plane. Okay, and I want to be able to decompose this y as a vector sum of two vectors, one that's a multiple to some given vector u, right, and one that's not. Now, I drew y first instead of u. Okay, you can forget that I did that, and you can say I drew u at the same time, or maybe you can even say u was first. Whatever, here's u. Okay, so here's our u, and here's y. Okay, and so I want to consider the problem of decomposing this y into a vector sum of a vector that is a multiple of u. Well, if it's a multiple of u, it lies on the subspace spanned by u. That is, it is, some vector parallel to u, right? It's a scalar multiple of u. And a vector z that is perpendicular to u. Well, maybe that z looks like this. Okay. And so, actually, the z that I'm going to consider stops here. So here's my z. Where's my y hat here? Well, if I take this vector as my y hat, this vector as my z, note y can be written as the sum y hat plus z. This z is perpendicular to u. Y hat is clearly a scalar multiple of u because it lies on that line determined by u. Okay. Okay. So this is exactly the thing that you have seen before, right? Because you could say, oh, well, doing this really, if you think about it, I have y already. If I can find y hat, then I'm good to go because since I already know y, if I can find y hat, then z is easy to find because it's just y minus y hat. Right? So I can always set z to be y minus y hat, and I'm good to go. Right? And so really the thing that I need to find in order to completely solve this problem is y hat, right? This is the thing that I have to find. Okay, well, finding this is finding this vector here, but what have I drawn here? I've drawn that Calc 3 projection of a vector onto another vector. Okay, that's exactly what's going on here. Now, of course, in Calc 3, this is all done in, R2, right? Or maybe, you discuss projection, in R3 in some way, although probably not. This is probably, maybe your Calc 3 class did like 2 examples of this at most and moved on. And so this was all done in R2, but I want to do this in Rn. Now, it can still help, of course, to visualize it in either R2 or to think about it in space, because that's all we can draw. But that's the idea. So I want to do this same kind of process, but I want to think about it in occurring in Rn instead. Okay, and so given any scalar, I can do exactly this thing. So I can notice that since I already know what y is, finding y hat is really all I need. So note if I set z equal to, say, y minus alpha times u, right, then automatically I get this thing, so I'm happy. And so now I just need to find this alpha, right? Since I know that y hat is a scalar multiple of u, I'm given u, I'm given y. All I need is to find that scalar, right, that scales my vector u. So all I need is alpha. Okay, but notice that, note once I've defined this, so note that y minus y hat is orthogonal to u if and only if what? Well, 0 is equal to, say, y minus alpha u. I'll write this as alpha u. Dotted with u. But, of course, this is the same as y dotted with u minus alpha times u dotted with itself. And I can do this by properties of the dot product, right? So dot product is distributive in this way, and then I can pull constants out of the dot product. And so this is what I get. I can solve for alpha here. What does this mean? So moving this to the other side and dividing, I get alpha is y dot u divided by u dot u. This is exactly what I had from Calc 3, right? Once I know what alpha is, I know immediately what y hat is, right? So y hat is y dotted with u over u dotted with u times times u, because it's alpha times u, yeah. And so there's the y hat that I've been looking for. And now I can easily write out what z is. Okay, and so z is just y minus y hat, which is here. Now, what is it that I'm saying here? Well, this is what we call the projection of a vector onto another vector in Calc 3, right? We're gonna have slightly different terminology. I mean, it's basically the same terminology, but it's more precise than our Calc 3 terminology because now we can see exactly what's going on here. So the vector. This vector y hat, I'm going to just go ahead and rewrite this here. So this vector is called the orthogonal projection this is called the orthogonal projection of y onto u. So this is exactly the same terminology as Calc 3 here. Okay, z is called the component of y orthogonal to u, or the orthogonal component, the normal component. So this is component of y orthogonal to u. Okay, and that can just be found by subtracting this y hat from y. Okay, but note, if c is any scalar, we could similarly project onto any scalar multiple of u, and we get the exact same thing. So we would get the same y hat. Right? So the projection of y onto u is the same as the projection of, say, y onto c times u. Right? And so this projection is actually not just determined by the vector u, right? So here's where the Calc 3 notion is a little, stops a little short when there's no need to, is that it's not the vector u that's doing it. In fact, any scalar multiple of u would have worked here, right? And so what really determines it is the subspace. So what really determines this projection is the subspace spanned by u. So we'll call that L. So it's the subspace L spanned by u. Now, why are we making such a big deal of this? Why are we making a distinction? Because this sets us up to talk about projections onto subspaces, not just projections onto vectors. Okay, and so really, this is an orthogonal projection onto the subspace L. Okay, so this is the projection of y onto L. We write that as the projection of y onto L, and this projection is exactly the same form as we wrote before. So this is called the orthogonal projection of y onto L. That's how you read this. So when I use this hat operator, that's what I mean. Okay. I know that some of you use hat for your vectors, so you know, this is one reason not to do that. Unfortunately, I wouldn't use this line for vectors. It's just that I can't write in boldface with a pen. Same thing if I was doing this on a board. I can't write in boldface on a chalkboard really in any way that's nice. So that's why I write lines to indicate that those quantities are vectors. And so the hat is the orthogonal projection operator in this sense. So this is what's nice about this and making a distinction here is because we want to set up the example or the precedent of projecting onto a subspace, not just a single vector. Okay, so let's do one example before moving on. What is the main in fact, this might have been the example that was done when you did this in Calc 3. What was the, or if you've seen this in physics, what was the main example of why you talked about orthogonal projection in this sense? It was decomposing a force, right? It was decomposing a force into its components. And so, for instance, if you were doing this composition, or if you thought about doing this composition, say on a curve, right? If you have some curve in space or some curve in the plane, then doing this was essentially breaking it into tangential and normal components, right? So the fact that you could do this nicely, I mean, okay, there's so many things that goes into this that makes this nice, so it's not just this that does it, but you could think about this as being breaking something into tangential normal components. Those are two nice, perpendicular. That's a nice perpendicular frame, orthogonal frame to consider. And that's one example of what's going on here. So let's do a single example of this, and then I'll move on to defining orthogonal matrices, and then we will move on to doing orthogonal projections on spaces of higher dimension. So what this is an orthogonal projection onto a subspace where the dimension of that subspace is 1, right? It's a linear subspace. Okay, so let's do a single example here. So let y be the vector 7, 6, and u be the vector 4, 2. So I want to project the vector 7, 6 onto the vector 4, 2. So find, I'm not going to write out all the words, so find y hat here. That is the orthogonal projection of y onto u. Okay. If written another way, if the span of u is equal to L, find y hat, which is the projection of y onto L, right? Okay. All right. Actually, I'll tell you what, so that I don't have to keep writing this stupid symbol over and over again, I'm just going to use hat. And when I use hat, just know that I'm talking about orthogonal projection. I'm not going to keep writing this. So if you see hat, that's not me calling that a vector. That's orthogonal projection. Okay, and so let's compute. What do I need to compute, right? So I already know that y hat is y dotted with u over u dotted with itself times u. So I just need to compute these two dot products and compute their ratio multiplied by u, and I'm done, right? So what is y dotted with u. Y dotted with u, so this is 7 times, so 7 times 4 plus 6 times 2. All right, so 7 times 4 plus 6 times 2. So 28 plus 12, so that's 40. And then u dotted with itself is 4 squared plus 2 squared, so 16 plus 4, so that's 20. All right, so this is 4 times 4 plus 2 times 2, which is 20. And so their ratio is 2. So y hat is equal to 2 times u. So this is 8, 4. Suppose, so then we could just check actually, so suppose now I was asked to find a vector z, right, that is orthogonal to u. How could I do that from this construction? Well, note that if I set z to be y minus y hat, that is, so y is 7, 6, y hat is 8, 4, then this is minus 1, 2, then z is perp to u. Let's just check. So if I dot z with u, what do I get? So this is, so here's z, here's u. So this is minus 1 times 4 plus 2 times 2. Hey, it is indeed 0. All right, so that is definitely perpendicular. Okay. All right. That's a simple example of how this works. Of course, you could have done this in any dimension. The drawing here, maybe I'll show you the drawing real quick of this thing. So this is a picture that shows this as if it were happening in R2. And the reason this drawing is nice is this drawing assumes that in the picture you're projecting onto some W instead of an L. Of course, you're still projecting onto an L in some sense, but yeah. So this is projection onto some subspace now instead. This is the picture. You'll see this picture again here in a little bit when we talk about orthogonal projection. Okay, but this is what's going on. Of course, this is happening in Rn, so this is just because we can only draw R2 or R3, but this is the intuition behind what's happening. Okay. All right, and so a couple of definitions, and then I'll move on. Oh, I don't know why I'm still out of focus. Oh, camera's still out of focus. There we go. Okay. So a couple of definitions here. So a set U1 to UP is an orthonormal set if it is an orthogonal set of unit vectors. So this is an orthogonal set of unit vectors. So vectors having length 1. Okay. So orthonormal is nice in the sense that I'm not going to just immediately say that it's the nicest form. So having an orthonormal set is the nicest form theoretically. Like abstractly, if you're writing letters for the vectors, it is as nice as it gets because, well, I mean, it's an orthogonal set, which is already really, really nice. But also, every single one of these is unit length, right? So maybe in your head, you immediately think of like the standard basis of Rn is an example of an orthonormal set and an orthonormal basis for Rn. But the thing is that, as you'll quickly see, and you might already think about this, going from orthogonal set to orthonormal set is not that big of a deal, right? Because if you have an orthogonal set of non-zero vectors, right? So if none of the vectors in question are zero, then you can always scale all those vectors by their length to turn them into unit vectors, right? And so the jump from orthogonal to orthonormal is not difficult to make. There's no depth there. Also, computationally, right? You might already think about this. Scaling vectors by their length. The length of a vector is typically nasty, and so scaling vectors by their length typically results in quantities that are ugly looking, right? And so this is not nice in the sense of for writing this out by hand, but abstractly it is as nice as possible. And so maybe I'll say here one more thing. So I'll say an orthonormal basis is exactly what you think. So if W is the span of that aforementioned set, then the set, whatever, I'll call this U, then the set U, or maybe S, since I'm going to use U in another way. So then the set S is an orthonormal basis for W. Okay. All right. And again, that's because it's already an orthogonal set, and if it's an orthogonal set, well, then it's automatically linearly independent. So if it spans the set, it's automatically a basis. Okay, and so now I have a definition that I want to make. So the definition I want to make is the definition of an orthogonal matrix. So definition. An orthogonal matrix U is a matrix whose columns form an orthonormal set. So an orthogonal matrix is not a matrix whose columns form an orthogonal set, so don't be confused by that. It is a matrix whose columns form an orthonormal set. Now again, based on what I said earlier, going from an orthogonal set to an orthonormal set is not a big deal. So note, going from orthogonal set to orthonormal set is trivial. Just scale each vector by its length. Why is that okay, right? Like why can I do that? Why can I scale vectors by their length and be happy? So the question is, if I have an orthogonal set, am I allowed to scale the vectors how I want? The answer is yes, by properties of the dot product, because I can factor scalars out of the dot product. If you have two vectors and they're orthogonal, if you take any two scalar multiples of those two vectors and dot them together, you still get 0, right? Because you could just pull the scalars out of the dot product's still 0. And so scaling vectors in an orthogonal set doesn't change the orthogonality properties. And yeah, so orthonormal and orthogonal, the difference is for an orthonormal set right here, it's an orthogonal set of unit vectors, right? So the difference between an orthogonal set and an orthonormal set is in an orthogonal set, the vectors are not necessarily unit vectors. Okay. So they may just be, they may just be orthogonal, right? Pairwise orthogonal, but they're not unit vectors. In fact, the examples we did of orthogonal sets weren't orthonormal. The only ones that were the standard basis, right? But this is an important fact. Don't overlook this. This tells you that if you have an orthogonal set, getting an orthonormal set's easy. You just scale each vector by its length. Okay. All right. And so, for instance, here's an example. Say that I have the set, say u1 is the vector, say 3, 1, 1. U2 is the vector, say minus 1, 2, 1. And U3 is the vector minus 1, minus 4, 7. Okay. So we can just check in our head real quick. If I do u1 dotted with u2, I get minus 3 plus 2 plus 1, so that's 0. If I do u1 dotted with u3, I get minus 3 minus 4 plus 7, that's 0. u2 dotted with u3, this is minus 1 times minus 1, so that's 1 plus 2 times minus 4, so that's 1 plus minus 8 plus 7, that's also 0. So this is an orthogonal set. So notice this is an orthogonal set. Okay. Now that I have this orthogonal set, what's an orthonormal set? Right. Well, I can just scale each vector by its length. So, right, define v1 to be u1 scaled by its length. So u1 over the length of u1. This is, 1 over the length of u1 times u1 if you like. So here's the vector u1. The length of u1 is what? It's square root of 3 squared plus 1 squared plus 1 squared, so it's square root of 11. So this is 3 over square root of 11, 1 over square root of 11, and 1 over square root of 11. All right. Okay. All right. And so V2 is defined similarly. So here's U2 divided by its length. Right. Okay. And so if I have U2 divided by its length here, then here's U2. Its length is square root of minus 1 squared plus 2 squared plus 1 squared. So that's square root of 6. So this is minus 1 over square root of 6, 2 over square root of 6, and 1 over square root of 6. And V3, I'm not going to write out what it is. It's U3 divided by the length of U3. So this is going to be, let's see here. So this is the length of U3 is square root of minus 1 squared plus minus 4 squared plus 7 squared. So that's square root of 1 plus 16 plus 49. So that's 66. So this is minus 1 over square root of 66, minus 4 over square root of 66, and 7 over square root of 66. Okay, so there's my 3 vectors, v1, v2, v3. Okay. Gustavo, you're saying once you have orthogonal vectors, say so say you're in R3 and you wanted to construct an orthogonal set of 3 vectors. Can't you just take cross product? Yeah, of course you can do that. So if you have 2 vectors and you want a third vector to form an orthogonal set of 3 vectors, then that's exactly what you can do. You can take the cross product in R3. But then what do you do, right? If you're in R4 or R5, right? So if you're in like R4 or R5, how are you gonna construct those vectors, right? You can't. So so this we are going to come up with an entire process called the Gram-Schmidt process that spits out orthogonal sets, starting from some basis. Okay. So anyway, we now have 3 vectors here that form an orthonormal set. They're still orthogonal. You can check if you really want to. we define them as we scaled each of these vectors by their length. Note that what this means, without even having to check, just algebraically, if I take the length of a vi, I get 1, right, for each of these. So the length of all these is 1. So all these are unit vectors. And so the set v1, v2, v3 is an orthonormal set. And now you see what I mean by it doesn't necessarily look the nicest, but it is a technically nicer set than the one you started with. Okay, because of this length property. All right. Okay, and so again, it is, even though this seems like a simple thing, it's important to remember this because there's just not anything extra you need to do conceptually here, right? It's just as simple as scaling by the length to go from orthogonal to orthonormal. So it's constructing the orthogonal in the first place that's important. Now, so I defined an orthogonal matrix. That is, in our example, thus, if I define U to be the matrix that has those 3 vectors as its columns, right? Then that matrix, I just write it out real quick. So this is 3 over square root of 11, 1 over square root of 11, 1 over square root of 11. The next column was minus 1 over square root of 6, 2 over square root of 6, and 1 over square root of 6. And then minus 1 over square root of 66, minus 4 over square root of 66, and 7 over square root of 66. Okay, so this, since v1, v2, v3 are an orthonormal set, then this is an orthogonal matrix. There's no such thing as an orthonormal matrix because it's an orthogonal matrix that is made up of orthonormal columns. Okay, what are the nice facts about this? Okay, so I'm actually going to stick to my promise not to prove this right now. Orthogonal matrices are really, really nice. We may return to this later in Chapter 2. Not Chapter 2, Chapter 7. But an m by n matrix, so an m by n matrix U has orthonormal columns So this has orthonormal columns if and only if U transpose U is equal to the identity. So this is a key defining fact of orthonormal matrices or orthogonal matrices. In fact, we could have, because it's an if and only if statement, we could have actually defined an orthogonal matrix in this way. Of course, when we talk about an orthogonal matrix here, really we want it to be square. So a U that is rectangular that has orthonormal columns like this, we wouldn't call it an orthogonal matrix because it's not square. If it's square, we call it an orthogonal matrix. So that's a minor point. You don't have to worry about that too much. But of course, automatically, this is just a more general statement. If U is n by n, it's an orthogonal matrix and it satisfies this property. Alternatively, if it satisfies this property, it's an orthogonal matrix if it's square. Okay, and the other very nice fact for orthogonal matrices is let U be an m by n. Again, this is a more general fact, but it's automatically true for orthogonal matrices. So let U be an m by n matrix with orthonormal columns. Let x and y be vectors in, say, Rn. Then a couple of things. So one, the length of U times x is actually the same as the length of x. This is really, really nice. This is a really, really important fact. This says that if U is orthonormal, for instance, or sorry, or if U has orthonormal columns, or or if U is an orthogonal matrix, so that M and N are the same, then if you consider the transformation defined by such a matrix that has such a matrix as its standard matrix, it preserves length, and there's a special name for that. It's an isometry. Okay. Secondly, ux dotted with uy is actually the same thing as x dotted with y. This is actually why it preserves the length, because it preserves the dot product. Okay. Okay. And 3, if you consider this transformed dot product again, and this thing is 0, this is true if and only if the dot product of x and y is 0. This really, all 3 of these, or I should say 1 and 3 follow from 2, really. Okay. Now these might just kind of look like random statements I'm throwing here, like they're not that important. These are really, really, really important facts that that these matrices satisfy. One says that length is preserved, which geometrically it says you're dealing with an isometry, which is nice as possible. 2 says the dot product is preserved, so for instance, orthogonality is preserved. If you start out with 2 vectors x and y that are orthogonal, transform those vectors by multiplying by u, you still get orthogonal vectors because the dot product is unchanged, so it doesn't affect the dot product. Another way of saying that is not just orthogonality is preserved, the angle between vectors is preserved. Okay, this also follows from the fact that you have u being an isometry here. And then 3 is just a special case of 2, really. So it's saying that if you start out with 2 vectors, right, that are orthogonal, that's what 3 is saying. If you start out with 2 vectors that are orthogonal, you get the transform vectors are also orthogonal, and vice versa here. Okay. All right. So this is a really, really nice. This is an orthogonal matrix. You can actually check if you really wanted to that this matrix satisfies all those properties, but I'm not going to do that. Okay, and so what is I have just enough time, I think, to get into the meat of this. So I'm going to leave orthogonal matrices right now, and like I said, I'll return back to this stuff conceptually a little bit later. But now we're getting closer to concerns or our ability to construct orthogonal sets. So Gustavo said, if you construct it of orthogonal and not orthonormal vectors, what goes wrong? So yeah, if you have a matrix that has columns that are not orthonormal, they're orthogonal but not orthonormal, well then basically what goes wrong is those things that you want to be true are just not necessarily true. So you need them to be orthonormal for those statements to actually hold. And there's nothing deep going on there, really. It's just that basically, for instance, if we go back here, the problem is that statements like this about preserving of length aren't true because the length is affected by the length of the vectors in question. That's why the length of all the vectors in question needs to be 1. And since the length of the vectors is not something that's important to us, we care that they're orthogonal to each other. We don't care what their length is, right? Like if I replaced in an orthogonal set, if I could replace every single vector by the same vector scaled by 500 million, I don't care about that. They're still orthogonal. The problem is that it would affect, as a transformation, it would affect, say, the length of the vectors, and I don't want that if I can avoid it. And we can avoid it by having their lengths all be 1. Okay, so the big named theorem that is our main step toward the Gram-Schmidt process, and also simultaneously a really nice fact is the orthogonal decomposition theorem. So I'm going to refer to this theorem by name a lot. So this is the orthogonal decomposition theorem. The main important thing to remember here is that this takes our earlier example of orthogonal projection onto a dimension 1 subspace and allows you to project onto any subspace you want to, okay, of any dimension. Okay, and so let's start out with that. So let W be a subspace of Rn. So let W be a subspace of Rn, then each Y in Rn can be written uniquely in the form Y is equal to Y hat plus Z, where Y hat is in W and Z is in W perp. Notice this is the exact generalization of what we were talking about before. You can go back and formulate exactly what we were talking about before in terms of this theorem because it's a special case of it. In fact, if U1 to UP is any orthogonal basis, we only need orthogonal here. Orthonormal is obviously even nicer because it's automatically orthogonal. But any orthogonal basis of W, then we can actually write out exactly what this Y hat is. Then this Y hat is just Y dotted with U1 over U1 dotted with itself times U1 plus and so on, Y dotted with UP over UP dotted with itself times UP. Okay. And Z is just Y minus Y hat. Okay. So there's my orthogonal decomposition theorem. Okay. This thing, this Y hat, there's what it is. There's Z. What is this called? So Y hat is called the projection. I'll usually just call it the projection. Technically, this is the orthogonal projection of Y onto W. And we write that Y hat is the projection of Y onto W. And when you see this, the orthogonal projection of Y onto W, this is what's going on in the background. Okay. Now I'm going to draw the picture of what's going on, and then that'll be all I do here. Actually, the proof of this is basically our nameless theorem applied a bunch. So that's basically what's going on. Kind of the same idea behind the nameless theorem. So what is the picture here? So the picture here is I have some subspace W sitting in my ambient space. Here, of course, this is in any Rn, but I'm doing it in space because I don't know how to draw 7 dimensions. So here's my 0, of course. W is a subspace, so it contains 0. Here's my vector y. Right, so here's y. And I want to write y uniquely as a vector sum y hat plus z, where y hat is a vector that lies in W, and z is a vector that lies in W perp. Okay, so if W is a plane, as in this picture, then Z is going to be some normal to that plane, right? And so the idea here is to find a vector that's in W. We'll see that intuitively this particular vector has a really, really nice interpretation as the closest approximation or best approximation of y to a vector that, or to a vector lying in W. I'll talk about that more on I'll talk about that more on Monday. So anyway, what I do here is I project down onto a vector y hat. This vector y hat is my projection of y onto W. And now I need a vector that is perp to W, lies in W perp. Well, that's this vector here. Right, Z, and to see that this is, a vector sum, I connect these dotted lines here to see, oh yeah, y is actually y hat plus z. And z lies in W perp. Z is perpendicular to absolutely everything in W because in this picture, W is a plane and z is a normal line or normal vector to it. Okay. All right, so that is intuitively what's going on. We'll do a few examples, and I'll talk about the best approximation theorem next time, and then we'll do the Gram-Schmidt process. So I'll go through the Gram-Schmidt process. I'll do like one example, and that will be Monday's class, and that will also be basically all of Chapter 6. I will mention least squares problems a little bit. I might do that I'll probably do that on Wednesday. And then Friday, I may start on Chapter 7, but your exam that I post on Friday will only go through the end of Chapter 6. Okay, so your exam won't cover Chapter 7. Anyway, so that's that. I'll start on Chapter 7, like I said, by Friday. You'll have discussion on Tuesday. Your discussion will involve the Gram-Schmidt process. So in your discussion section, you will do Gram-Schmidt. Remember, you have homework due on Monday as well. So I'll assign a new homework set on Monday. And I think that's it for now. So actually, I don't know if I'll assign a new homework set or not. I might, since you're going to have an exam on Friday, I might just put what I would have put on that homework on the exam. So anyway, that's the plan. So I will see you all on Monday. I'll have more office hours next week, probably on, we'll say Wednesday. So anyway, that's the plan. So anyway, I will see you all next week. See you on Monday.